Welcome to today's webinar about how safe, efficient, and comfortable are wearable antennas. My name is Amin. I am RF Application Engineer at EMWorks. This is a brief overview of the presentation. So first we'll talk briefly about telemetry and wireless body area networks, or WBAN for short. Following that, design challenges and proposed solution will be presented. After that, we will talk about the antenna design and some of the simulation results. At the end, we have a live demo. So in case if we have any questions, I will be happy to answer them at the end of the presentation. Alright, so let's talk a little bit about biotelemetry. What is telemetry? Telemetry simply means the data collection being made at a distance. Psychological data, it could be collected by medical devices which are placed on the human body. Biotelemetry, it has several advantages. For example, it can be used to monitor patient vital signs such as a pulse and respiration. It can also allow patients to move freely, so basically the patients are not restricted to bedside with the hardwired connection. In this image we can see a picture of a guy called Bob. So basically in 2019 Bob had serious face injury, as you can see from this image. And thanks to his Apple Watch, he was able to receive the medical assistance in 30 minutes. So from this incident we can see the importance of the biotelemetry. So now we talked about biotelemetry. So for biotelemetry, in order to send the data that I collected, it can be done through wireless or it can be done wirelessly through the wireless body area network. So what is a wireless body area network? Wireless body area network is simply a network that is composed of low power micro and nanotechnology sensors and actuators. It has several benefits. For example, it can allow the patient to be more mobile and active without the wired devices. For instance, patients in the hospital, they can move out of their beds and they can even move in their room, or they can even go out of the hospital for a while. It can also allow physicians to get critical psychological measurements in the patient natural environment. So, for example, if the patient is still moving, the physician, they can still receive the measurement. In this image, we can see a patient that has the wireless body area network, and the wireless area network is composed of several sensors that are used to measure certain biological functions, such as the temperature, blood pressure, electrocardiogram, ECG, heart rate, and respiration. After that, the data are being transferred wirelessly to a body control unit, or BCU. So now we talked about the biotelemetry and some of its advantages. Now let's talk about some of the design challenges. For each wireless system, of course, we need to have an antenna, and biotelemetry is no different. Placing an antenna near a human body can have a great effect in its performance, and this is due to the dielectric loading. So basically the human body is considered as large lossy dielectric material and can have a big effect on the performance of the antenna. The other thing is, we want the back radiation of the antenna to be as minimal as possible to avoid overheating or damaging the biological tissue. Of course, we want the antenna to be flexible and very small to make it more comfortable for the patient. In order for the antenna to be safe for the patient, there are certain SAR limits which has to be followed. In this table, we can see different SAR limits which are set by Federal Communications Commission, or FCC. For instance, for the partial body, it has limit of 1.6 for the uncontrolled exposure time, but for the controlled exposure time, it has limit of 8. Alright, so let's talk a little bit about some of the proposed solution. So in order to prevent the back radiation and also to enhance the gain, reflectors is used. So for example, the reflector, it can help improve the gain as well as preventing the back radiation. For the reflector, we can use a perfect electric conductor or artificial magnetic conductor, or IMC. For perfect electric conductor, so we need to place the reflector at a distance of quarter wavelength. But the problem with this is that at low frequency, quarter wavelength becomes very large. So now the antenna becomes very bulky to wear. So as an alternative for this, we use what we call the artificial magnetic conductor. By using the IMC, the distance between the antenna and the reflector can be significantly reduced. In this image, we can see for the perfect electric conductor that is placed at λ/4, so to have constructive interference. But the problem with this is at low frequency we have large distance, and this makes the antenna very bulky. Instead, we have the artificial magnetic conductor, which is placed at a distance is much smaller than the wavelength, and this makes the antenna very small and comfortable for the patient. This is the antenna that we are going to study today. It's basically a slotted dipole antenna. So first we'll talk about the slotted dipole antenna without the IMC reflector. The antenna is designed to operate at 2.5 gigahertz. The substrate material is Rogers 5850 with permittivity of 2.2 and loss tangent of 0.009. So basically it's low loss material. The antenna has dimensions of 89 millimeter by 83 millimeter. At the bottom left hand side we have a picture of fabricated slotted dipole antenna. On the right hand side we have the picture of the simulated antenna. A is the top view and B is the bottom view. This is some of the results we got using HFWorks. So first let's start with the return loss of the slotted dipole antenna. As we can see from this figure, the antenna resonates at 2.5, and this is somehow matches the measurement. So at 2.5 the antenna has a return loss of almost minus 15 dB. In the middle we have the picture of the mesh. On the right hand side we have the animation of the electric field at 2.5 gigahertz. In HFWorks we have what we call the antenna far field results table. Under this table we can see different antenna parameters. So for example, from this table we can see the maximum gain, mismatch efficiency, radiation efficiency, total efficiency. So for our antenna, so we can see it has a gain of 4.7 and total efficiency of 96%. At the bottom we have the 3D gain pattern of the antenna. So from this plot we can see the antenna has a broadside radiation, and also we have some backward reflection. Looking at the 2D radiation pattern, we can see that the antenna has some omnidirectional radiation, and also again has the gain of 4.7. So for us we want to make the radiation unidirectional instead of omnidirectional. Also we want to minimize the back reflection. Okay, so now let's see what would happen if we add the IMC reflector. So again we have the same slotted dipole antenna, but in this case we just added the rectangular patch IMC. So for the rectangular patch IMC, it has substrate materials of Rogers 5850 with permittivity 2.2 and loss tangent of 0.009. So the height of this substrate is 0.8 millimeter. So the spacing between the antenna and the reflector is 1 millimeter. So for example, if we were to use the perfect electric conductor, now its spacing at quarter wavelength for the frequency of 2.5, it becomes 30 millimeter. So we can see from here that the importance of using IMC and how it can help reduce the spacing. So in this example we almost decrease the spacing by a factor of 30. At the bottom left hand side, So we can see the picture of the fabricated slot dipole antenna with rectangular patch AMC. So this is our slotted antenna, and this is the rectangular patch AMC. Looking at this bottom graph, this is the side view. So on top we can see an antenna that is you can see the antenna on top of the substrate, and there is air spacing of 1 millimeter, and underneath of the antenna we have the AMC reflector. So first let's look at the return loss of the antenna. From this figure we can clearly see there is big enhancement in terms of the return loss. So at resonant frequency is almost 2.52. The antenna has a return loss of almost -26. From here we can also see there is a slight shift in terms of resonant frequency. Looking at the antenna far field results table, we can see the antenna has you can see there is a big increase in terms of the gain. So the antenna has a gain of 7 dB and total efficiency of 97%. So we can see now the effect of AMC in terms of enhancing the gain as well as enhancing the return loss. So by looking at 3D gain pattern, we can see we have now broadside radiation, but now we have some backward radiation, but this is reduced as compared to the previous scenario. By looking at the 2D gain pattern of the both scenario with AMC and without AMC, we can see there is a big increase in terms of the gain pattern, and also we can see now the back radiation now gets reduced. Also now we no longer have the omnidirectional pattern, so we have the unidirectional radiation. So again, AMC helps significantly reduce the back radiation and improve the forward gain. Okay, so let's look what would happen to the antenna when it's placed near the human body. So as an example, we'll use the human arm. So from this picture, we can see there is a human arm. At a distance of 2 millimeter, there is the slotted dipole antenna. By looking at the graph in the left hand side, so we can see that there is a shift in terms of resonant frequency, and also there is a big effect on the return loss. At resonant frequency we have return loss of almost -5 dB, so our antenna no longer operates as desired. So the reason for this now, because now since we have the human arm, which is we can think of it as the dielectric material, and this dielectric material affects the near field, and since it affects near field, which in turn can affect the return loss and radiation pattern. By looking at the SAR, we can see that the SAR exceeds the SAR limit of 1.6. So we can see that our antenna is no longer safe for the human body. Looking at the 2D radiation pattern, we can see there's a big decrease in terms of the radiation, in terms of the gain. So now we have the gain of almost 2 dB. Alright, so let's see what would happen if we add an AMC reflector. So again, we have the same human body model. So now we added the AMC layer. So again, the antenna and the reflector are at a distance of 2 millimeter. From this figure, we can see there's a bit of shift in terms of the resonance frequency, but also there is big decrease in terms of the return loss. So previously the return loss at resonant frequency, it used to be minus 5 dB. Now at resonant frequency we can see the reflection is almost minus 22 dB. So we can see the effect of the IMC and how it helps to reduce the effect of the dielectric loading of the human body. Alright, so let's look at the SAR. So from this plot we can clearly see that the SAR level is 0.03, is far beyond the SAR limits. So we can see now the antenna is safe and is safe for the patient. So by comparing the radiation pattern of the antenna with and without AMC, so we can clearly see there is a big increase in terms of the gain. So previously we had a gain of almost 2 dB, and now we can see the gain gets enhanced further to almost 8 dB. Also we can see there is a reduction in terms of the backward radiation. Alright, so now we have a live demo. We'll be showing you how to design such antenna using HFWorks. This is HFWorks and this is SolidWorks. HFWorks is fully embedded in SolidWorks. Once you are done creating your geometry in SolidWorks, you can just go ahead and start your simulation in HFWorks. HFWorks is also gold certified by SolidWorks, so it's simply just a tab. In HFWorks we have 4 types of study. So we have antennas, S parameter, TDR and resonance. But today we will focus on the S parameter. In HFWorks, almost for each study we have 3 main steps. So the first step is to define the accuracy, the frequency range, also the meshing, manual, adaptive. So if you know how to use the mesh, you can use manual, otherwise you can use adaptive, and the software will figure it out for you. You can also do the thermocoupling. The next step is to apply material. To apply material, you just right click, say apply material. So we have different material under material library, and also different material from different vendors, for example Mitsubishi, Rogers, and so on. Next is the setup of the boundary condition. So we have different boundary conditions. We have ports, lumped port, PEC, PMC, PEC symmetry, PMC signal. The last step is kind of optional. So if you know how to do the mesh, you can apply mesh control. You can apply mesh control on bodies, faces, edges. You can also specify the element size. Also, if you want to find out more how to do simulation in HFWorks, you can always follow up our YouTube channel, emworks.com. Alright, so let's talk a little bit about the slotted dipole antenna. So this is our antenna. This is basically slotted dipole antenna. So this is the connector. So this is the mesh of the antenna. In HFWorks we have what we call the results table. And the results table we can see different circuit parameters such as generalized S matrix, renormalized S matrix, impedance matrix, admittance matrix, port result, VSWR. You can print versus current frequency or frequencies. You can also export results to different formats such as text file, CIT, SPC or touchstone. So let's look at the return loss. So from this figure we can clearly see that the antenna resonates at 2.5 with the return loss of almost minus 15 dB. So, and this corresponds to the measurement. So let's look at the antenna results table. So in HFWorks, as we said before, we have the antenna far field results table, Under this table we can see different antenna parameters, such as the maximum gain, mismatch efficiency, radiation efficiency, total efficiency. So in our case, our antenna has maximum gain of almost 4.7 and total efficiency of 96%. So let's look at the radiation pattern of the antenna. So from this spot we can see we have broadside radiation, and also we have some backward radiation. So this is the 2D radiation pattern. We can see now the antenna has a kind of omnidirectional radiation. So our aim is to have unidirectional radiation. Also, we want to minimize the backward radiation. So let's look at the electric field distribution. In HFOX we can see the electric field distribution as well as the magnetic field distribution. We can even animate the electric field. So from this you can clearly see the animation of the electric field. Alright, so let's see what would happen if we add the AMC reflector. So this is the slotted dipole antenna, and underneath it we have the AMC rectangular patch. So the spacing between the two is 1 millimeter. So let's look at the return loss. So from this figure we can see there is slight shift in terms of the resonant frequency, but there is big enhancement in terms of the return loss. So we can see the return loss get reduced from almost minus 15 dB up to almost minus 26 dB. So now we can see that there is a big effect of the AMC in terms of the return loss. Looking at far field results table, we can clearly see that the antenna has maximum gain of 7 dB and total efficiency of 97%. So let's look at the 3D gain pattern. So here we have the broadside radiation and some of the backward radiation, but now it gets reduced. So looking at the 2D gain pattern, we can see there is big increase in terms of the gain, and also the backward radiation gets reduced as compared to the case without AMC. Alright, so let's see what would happen if we put the antenna beside the human body. So this is the human arm. At the distance of 2 millimeter, we have the slotted dipole antenna. From the return loss, we can clearly see there is a shift in terms of resonant frequency, and also we can see now at resonant frequency you can see the return loss gets decreased to minus 4 dB. So our antenna no longer operate as desired. So looking at the far field table, we can see there is a big decrease in terms of the gain. So now also in terms of the total efficiency, so our antenna has total efficiency of 16%. So let's look at the 3D gain pattern of the antenna. So again we have the broadside radiation pattern, and also we have some backward radiation. Okay, so let's look at the cell level. So from this figure, we can see that the cell level exceeds the standard limit of 1.6. So from here we can see that the antenna is no longer safe for the human body. Alright, so let's see what would happen if we put now if we add the AMC layer. So again, we have the antenna and the AMC layer that are at 2 millimeters away from the human arm. So looking at the return loss, we can see that the antenna has a bit of shift in terms of the frequency. So now the antenna now resonates at almost 2.68, and at the resonant frequency we have return loss of minus 20 dB. So you can see there's big enhancement in terms of the return loss. So looking at the far field results table, we can see that the antenna now has maximum gain of 8.6, and so you can see there is big increase in terms of the gain, and the antenna has total efficiency of almost 43%, and this is still within the standard limit. So this is the 3D gain pattern of the antenna. So we have the broadside radiation and the gain of 8.6. So we can see now the back radiation gets reduced. So by comparing both the antenna with and without AMC, so we can clearly see there is a big increase in terms of the gain, and also the back radiation gets reduced, and this is because of the AMC. Alright, so now let's look at the SAR level. So from this figure we can see now the SAR level is far beyond the standard limit of 1.6. So now the antenna is safe for the human body. So in our case it's the human arm. Here comes the end of the live demo. To summarize, we have seen the importance of using artificial magnetic conductor and how it helps minimize the back radiation and improve the forward gain. IMC can also reduce SAR level to the standard limit. We have demonstrated how easy and powerful HF work is and how it helps designers to ensure antennas are safe, efficient, and comfortable. So with that, I would like to thank you, and now the floor is open for questions. Thank you.